Today we're going to graph square root and cube root functions. The parent function for the family of square root functions is square root x, and for cube root is cube root x. Notice the patterns that the vertical stretch or the rise affects this root graph. To the right of 0, 0, we rise 1, which is a. To the left of the starting point, we have no values. That is because we can't take the square root of a negative. So my domain is only the numbers we can take the square root of, which would be 0 inclusive up to infinity. If there was a horizontal shift or a reflection, that would change this domain. The range is all our y values, which would also be 0 inclusive up to infinity. Even though it's only increasing ever so slightly, it still does increase to infinity. For cube root of x, let's call this inflection point our starting point. Notice the pattern of the rise, or the pattern of a, from the starting point. We move 1 unit to the right of the starting point and rise again 1 unit, which is a. But the difference for cube root is that when we move 1 unit to the left of the starting point, we rise negative a. That gives us 3 points, which is enough to graph a cube root function. Your domain for this is negative infinity to infinity. It goes on forever and ever. And your range is also negative infinity to infinity. Again, it's increasing ever so slightly, but still increasing until infinity. And if you had any sort of vertical or horizontal shift, this starting point would be known as hk. We can use these transformations to graph instead of plugging in a table of values to make it more efficient. For number 1, graph each function and identify the domain and range. I'm not a huge fan of the fact that this is a horizontal stretch rather than being written as a vertical shrink, so I'm actually going to rewrite knowing what I know about radicals. The square root of 1/4 is 1/2, so this can be rewritten as 1/2 square root x. Because we do not have a horizontal or vertical shift, our starting point, or our hk, I'll call it our initial point, or IP in this case, is 0, 0. And our vertical shrink is 1/2. And we remember that this is a square root function, so the shape should be like this. 1 unit away from the initial point, I will rise a, which is 1/2. And that's enough to graph a square root function. Because our initial point is 0, 0, our domain is still 0 to infinity, and our range is still 0 to infinity. This 0 is our h value, this 0 is our k value. For part B, our inflection point is still 0, 0 because we have no horizontal or vertical shift. Our vertical stretch is -3. This is a cube root function, so its domain and range will always be negative infinity to infinity. 1 unit to the right of the inflection point, we need to rise -3. 1 unit to the left of the inflection point, we need to rise the opposite of -3, which is +3. And remember, your options for a cube root would look like this or this. So there's my function. Remember, the negative was a reflection in the x-axis, which is why this cube root function steadily decreases when the parent cube root function steadily increases. Now for part C, h is equal to 5 and k is equal to -2. We have a cube root function, so our inflection point is 5, -2, and our vertical shrink is 1/2. Because we have a cube root function, the domain and range will always be negative infinity to positive infinity. Graph your inflection point. 1 unit to the right of the inflection point, we rise 1/2. 1 unit to the left of the inflection point, we rise -1/2. And here's our graph. For part D, h is -1 and k is +3. So my initial point will be -1, +3. A is equal to -2. Graph your initial point, and 1 unit to the right of the initial point, you will rise -2. So go down 2. So here's our graph. Remember, domain is dependent on h. So it goes from -1 inclusive to positive infinity. The range is dependent on k. And because this root graph is decreasing, we start at negative infinity and go up to the k value inclusive. For number 2, write the function g of x given the transformations of f of x. For part A, g of x is going to be f of x translated 3 units to the right. To go to the right, we're going to subtract 3 from the x. And there's g of x. For part B, we need to vertically shrink cube root x by 1/2. A vertical shrink should be multiplied by the entire function. And there's my answer. This time, they already wrote the transformation algebraically. Plus 2 inside of the function is left 2, minus 1 outside of the function is down 1. Add 2 to the x and subtract 1 from the entire function. If there had been a statement that said vertically shift up 10 and then vertically shrink by 1/5, this would not be our answer. We would need to multiply everything by 1/5 after adding 10. For part E, we're going to horizontally shrink by a factor of 1/6 and then translate 3 units to the left. So I'll write k of x as the horizontally shrunk function and then move that one 3 units to the left. To horizontally shrink by a factor of 1/6, we need to multiply the x by the reciprocal, which is 6. Making our horizontally shrunk function cube root of 6x. Now let's translate 3 units to the left by adding 3 to the x value. Making g of x cube root of 6x plus 3. For number 3, use a graphing calculator to graph 1/2 y squared equals x. Identify the vertex and the direction that the parabola opens. Now, the beautiful thing about Desmos is you can type this directly in and see the graph. But the thing about a graphing calculator is that it needs to be in terms of y. The problem here is that we have a y squared, so we need to solve for y in order to graph using a graphing calculator. That is very useful because you are able to use a graphing calculator on the AP Calculus exam. So begin by solving for y. Now we have two equations where y is in terms of x. Y equals positive root 2x and y equals negative root 2x. Type these into your graphing calculator as two separate equations to get the entire graph. And here's what your graph looks like. Okay, so our vertex turned out to be 0, 0. And our parabola opens up to the right side. 1/2 y squared equals x is not a function because it does not pass the vertical line test, which is why on a graphing calculator, to see the entire graph, we have to write it as two separate functions. y1 is equal to the top root function, and y2 would equal the bottom root function. And that's graphing radical functions.